So today I'll be presenting the paper titled Generative Adversarial Graph Convolutional Networks for Human Action Synthesis. There are two main categories of skeleton-based human action syntheses. The first one is autoregressive, and one of the main models that the authors compare their model against is in the paper titled Recurrent Network Models for Human Dynamics, which introduced encoder-decoder network architecture with LSTM. The second one is auto-conditioned recurrent networks for extended complex human motion synthesis, which proposed a conditioned LSTM network. The authors argue that these models, autoregressive models, come with their own limitations. The first is the structural limitation. These autoregressive models struggle to optimally extract and utilize the inherent structural information of the body from vectorized skeleton sequences, which leads to suboptimal results. The second limitation is temporal dependency issue. Frameworks like LSTMs, GRUs, and sequence-to-sequence models face scalability issues when dealing with bidirectional temporal dependencies. These dependencies involve feature frames potentially modifying past ones and a difficulty of past frames conditioning distant feature frames. The second category is generative. So these are the methods that mainly incorporate generative adversarial network into human action synthesis tasks. There are two main ones that are cited in my paper. The first one is titled Unsupervised Feature Learning of Human Actions as Trajectories in Pose Embedding Manifold. In this paper, authors propose a hierarchical feature fusion method using an RNN autoencoder architecture that includes a manually structured tree of limb connections. And the second one is titled Structure-Aware Human Action Generation, in which authors suggest enhancing an RNN with a graph convolutional network to better analyze latent temporal dependencies. But these also come with their own limitations. So despite their advantages, many of these GAN-based methods continue to use manually structured vector sequences like this one to model skeleton data, which can be restrictive. Additionally, these methods often incorporate autoregressive techniques and Gaussian processes to manage long-term relationships in the latent space, which still limits scalability and flexibility in action conditioning. So what is the format of the data that the model in my paper accepts as input? So the graph is represented as a tuple of vertex set and edge set. In this context, joints are vertices so each of the vertex set has NL nodes, and we also have TL frames at each of the resolution levels. But the data set does not come with edges. So how are they constructed? The edge set is union of two subsets. Joints within one frame are connected with edges according to the connectivity of human body structure. So these are the blue edges that you can see between the blue vertices. So this figure is frame 1, for example. And then each joint is then connected to the same joint in a consecutive frame. So these are the green edges that you see between temporal frames. To briefly talk about the model and how it works, unlike typical generative-based action synthesis methods that use a sequence of latent vectors combined with autoregressive techniques or Gaussian processes, this approach generates a human actions from a single latent point Z. This method contrasts with previous methods that often result in entangled factors of variation due to multiplicative interactions across a latent sequence. The generator begins by transforming the latent code Z from the latent space Z through a nonlinear mapping network. This process produces an intermediate latent space W, which aims to disentangle the latent factors more effectively. The transformation is designed to increase the linearity of factors of variation, making it easier for the generator to produce realistic actions. The effectiveness of this approach in reducing entanglement was confirmed in previous image modeling studies, but the authors of this paper further investigate this in ablation study. So there are two further things to consider. The first one is spatial upsampling. The generator first performs spatial graph upsampling, which involves introducing new vertices into the graph at each frame and assigning them average values from connected joints, gradually increasing the spatial resolution of the generated actions. The second one is temporal interpolation. Along the temporal dimension, one-dimensional interpolation is used to expand the number of frames in the skeleton sequence, enhancing the temporal resolution. In terms of discriminator mechanism, its role is to differentiate between synthesized and real actions, which does this by gradually coarsening the input skeleton's graph. This coarsening involves removing vertices and reconnecting the remaining neighbors, thus simplifying the graph structure as part of its assessment. The authors used two main metrics to compare their results against the previous state-of-the-art methods. The first one is Frechet inception distance, which measures the distance between the real data distribution and the synthesized one. The second one is maximum mean discrepancy, which measures the discrepancy between real and synthetic samples based on a two-sample test to measure the discrepancy of both distributions. So the authors used three data sets. The first one is NTU RGB-D, and the second one is NTU 120 RGB plus D, and the third one is Human 3.6M. The first one only contains 60 actions. The second one contains 120 actions. And they used the state-of-the-art models at the time of the publishing of this paper to compare their performance against. Such as skeleton VAE, skeleton GAN, CGAN, and SAE-GCN. And as we can see across all metrics, this method outperforms the other methods. Thank you.